we'll see one by one. The first exercise is a very simple one. So you have to simulate a simple sample and hold circuit, and you have to apply a sine input of 1 kilohertz with 200 millivolts peak to peak over a DC voltage of 0.1 volts. Then you have a sampling clock of 10 kilohertz with 1.8 volt to be high and 0 volt to be low. So you should plot the output on node voltage 2. So the main objective of doing this particular exercise is to see the effect of charge injection as well as clock feed through. Okay, so let us simulate this sample and hold circuit now. So you can see that, so you can zoom here. So you can see the held value, it is actually decreased. Okay, so because of the, I think you can see it. So because of the effect of charge injection and clock feed through, there is a significant error in the held value. Okay, so this is the drawback of a simple sample and hold circuit. So in order to overcome this particular drawback, so we go for some other type of sample and hold method. So the next thing will be sample and hold circuit with the bottom plate sampling. So I think you know the working principle of this bottom plate sampling. So clock 1 and clock 2. Clock 2 will be the advanced version of this clock 1. So again in this exercise, so what you have to do, you should plot the voltage on node 2. So, and you should see whether this particular technique has any effects of charge injection as well as clock feed through. Okay, and in the exercise what you have to do is you should vary the delay. So don't give any delay between clock 1 and clock 2 and see how exactly the outputs on the node 2. Okay, that is what you have to see in this particular exercise. So let us simulate this particular circuit, that is the sample and hold circuit with bottom plate sampling. Okay, so you can see here the clock 1, that is V6 is the advanced version of V3. Okay, so the clock 2 is your V6 and clock 1 is V3. I think that is visible here. Yeah, so this is visible. So this is what the advanced version, so how the clock is applied. And if you see the output, so yeah, so the output you can see here. So there is not much change. So compared to the simple sample and hold circuit, there is not much significant change here in the held value. Okay, so in this way the sample and hold circuit with bottom plate sampling techniques can improve your a sample and hold circuit. Okay, so when the MOSFET is turned off, the effect of charge injection and clock feed through is reduced. So this is one type of a sample and hold, better sample and hold circuit compared to the simple sample and hold circuits. So there are other circuits also, so which you can explore. Next part is the exploration of switched capacitor circuits, where we are going to implement a resistor with a switched capacitor network. So this is the schematic for that. Okay, so you have to simulate the switch capacitor resistor, and there are two voltages V1 and V2 with 0.6 volts and 0.4 volts, and the clocks which are applied here are non-overlapping. Okay, you can see here those clocks are non-overlapping in nature. So first exercise is you have to measure the current through voltage V1A and evaluate the resistance which is emulated by the circuit. So in this particular circuit, so you have to measure what is the current flowing through this particular switch. Okay, M1 switch, or the voltage that is the current through V1A. Okay, with through this particular current. So this current, and you have to measure the average current. Okay, average current flowing through the switch M1. Okay, and also we know that for this particular switched capacitor circuit, the equivalent resistance R is given by R is equal to T divided by C1. Okay, so R is equal to C divided by T1. So the T here we have used is 10 nanosecond. Okay, the duration is the pulse duration, the pulse frequency is clock frequency is 10 nanoseconds, and the C1 comes is we have used for the simulation is 1 picofarad. Okay, so by this, so what is the estimated, so what will be the value of R here? So R is equal to T divided by C1. T is equal to 10 nanosecond, C1 is equal to 1 picofarad. So the resistance comes around 10 kilo ohms. So the first exercise is, so theoretically we have found out that R is equal to 10 kilo ohm. Now we have to calculate what is the average current flowing through the switch M1. Okay, so let us do that. So let me simulate this MOS resistor. Okay, so I have not plotted anything, but I have used a dot measure statement. You can see the netlist and you can see how to measure the average value. It is given in the netlist. So the average current which is flowing through the switch is approximately 20 microamperes. Okay, 20 microamperes. So now, so you have to compare whether the resistance what we obtained theoretically, is it matching with this particular, is it the capacitor, is it the resistor which is emulated by this particular circuit is same as the resistor which is given here. Okay, so we know that the voltage V1 here is zero point 0.6 volts and voltage V2 is zero point 0.4 volts. So the what will be the current here? I is equal to, if we take, if from our calculation from exercise A, we found theoretically R is equal to 10 kilo ohms, correct? So this R is 10 kilo ohm, this V1 is zero point 0.6 volts and this V2 is zero point 0.4 volts. So the current flowing will be around 20 microamperes, correct? So whatever this particular circuit, that is the average current which is flowing through this particular circuit, is say it is equal to the current through the this particular circuit, which means my R, whatever the resistor emulated by switched capacitor circuit, it is matching with the this particular circuit. Okay, so in the next exercise what you have to do is, you must vary the clock period, you must vary the value of C1 and observe the and calculate the value of R, and you have to verify the value whether it is matching with this particular circuit, and also apply different values of V1 and V2. Okay, so that should be a next exercise. So in the fourth exercise, that is, you must build an integrator. So as you can see, there is a resistor here. So this resistor which we have just seen now. So this R, and you have integrator here. So when you connect an R with a C, it behaves as an integrator. So again the same thing, this clock 1 and clock 2 are non-overlapping clocks. So first implement this particular circuit with an ideal op amp. Okay, and then you observe the behavior of the integration operation. Next, you can use the practical op amp, watch what we have designed in day one, and use that particular op amp and see the behavior. Okay, so you can explore all those things. So any doubts in this thing, exercises, please let me know if you have any doubts.
Hello.
Yes, sir.
V1 and V2 values can be arbitrary. We have to select, or some specific range we have to take V1 and V2.
Sir, it depends upon the supply voltage, the whatever you're using. So here maximum using like 1.3, 3.3, right? So the MOS has to be turned on, right?
Yes, yes.
So depending upon those things, you can select your values of V1 and V2, sir.
Okay.
Yeah. So in this case, the supply voltage is 1.8, Mayur?
1 point, yes sir, 1.8.
1.8, and the threshold voltage is around 0.4.
Point 4.
So that brings it to 1.4. But since the source and substrate are not at the same potential because of substrate bias effect, another 0.3, 0.4 volts VT shift will be there. So roughly up to 0.8, 0.9 volts, it should work well. V1, V2 between 0.8 to less than 0.8 and 0.9 also should work well. Because beyond that, substrate bias effect and of the transistor starts acting, and that will limit the conduction.
Okay, sir. Okay.
Hello, sir.
Yes ma'am, yes ma'am.
Sir, can you go to the result of first exercise? Okay, sir. Here you mentioned that the hold value is not
Yeah.
means.
Huh.
So I didn't get that. So what is that exactly?
What you're actually getting in
Mayur,
this.
just zoom in at one of the sample locations. It's so
Here, red one is
when
the
it is
sampled. So red one is the.
this
Uh,
the red flat region of is the sample value, when it actually should have been somewhere close to 180 millivolts. It should have sampled at 180 millivolts, but because of the clock feed through and charge injection, you are getting a shift of almost
okay.
35 millivolts or so.
Okay. Okay. So this drawback we have minimized in the second case.
Yes, 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 yes ma'am.
So in second case we have got almost near.
Yeah, yeah,
Okay.
May you just show the second one again?
yeah.
Maybe you can zoom in some close to a sample value now. Just maximize it. Yeah. So you see now the error is like less than 1 millivolt or so.
Yes, sir. Yes, sir. Understood. Okay. So, sir, this will be this small error will be there always, right? 1 millivolt. That is acceptable.
Huh.
Well, with bottom plate sampling, we
Ah,
can reach there, but if you use more sophisticated circuits, which we have discussed, you can even bring that down.
Yeah,
So
so again, this can be further reduced with better circuits.
yeah, yes,
yes,
yeah,
see,
yes,
the
yes.
bottom plate sampling only corrects for the charge injection. It doesn't correct for clock feed through. So
Oh,
the clock feed through is a constant offset. Maybe by using some of the other circuits that we discussed, we can even go to a smaller value of sample error.
okay.
These are
So, are we,
two very basic circuits, bottom plate sampling and the simple sampling switch that we have shown here.
so, sir, are we simulating any circuit to reduce the clock feed through effect?
In this, no, but small modifications you can, for example, adding a simple dummy transistor. It's a very small modification. You can try those things.
Okay.
Just by adding the dummy, yesterday we discussed, right? Dummy switch compensates for clock feed through also. We can just try that, put that dummy switch, and you will be able to see. See,
Okay.
if you
Okay.
recall, the bottom plate sampling does not reduce the offset completely. It only makes the charge injection independent of Vn. There is always a residual charge injection, which is a fixed amount. So that fixed offset is what you are seeing here. It's not
Okay.
a nonlinear offset, it's a fixed offset, is what we are seeing. By using the other dummy sampling switch and other techniques, you can even bring that down.
Okay, sir.
So please simulate the circuits and try out the exercises. And this particular topic of sample and hold circuits is not very sophisticated in terms of circuit complexity. So adding one more dummy transistor, trying those 4 switch combination, whatever we have discussed, requires very small changes to the netlist. So you should be able to do that very easily. Unlike the other circuits wherein you have to design a lot, and I mean it takes a lot of time to design and write the netlist for the big circuit and all. These are simple circuits. So I would encourage all of you to simulate the given netlist and try out small variants of the circuits that we have discussed in the yesterday's session.